Hello, scholars. This is Sample Means, section 7.3 in your book. As you recall, we did some examples in class. One is we took all the values of the miles from Del Lago that each scholar in our classes lives away from Del Lago. And the top blue graph is the population distribution. So each dot represents a person in our classes, in our AP Stats classes, and the distances they live from Del Lago. And you'll notice that there was one outlier. And then the orange graph shows when we took samples. So we took a sample of size 5 and we found the average distance in that sample of size 5. And you'll notice that when we took averages, something happens to the distribution. So even if one of the values in that average or in that sample was the outlier, the fact that you have other values in there that average out tend to make the values cluster more towards the middle. So by averaging it out, we have values that are less variable and cluster more towards the middle because the smaller values balance out those larger values. And if we take an even bigger sample size, like in the green graph, which is samples of size 15, the effect of the outlier in those graphs is even less. So we can see that. Also, all three of the graphs are clustered around the true population average, which is mu equals 4.79. So on average, the scholars in our two AP Stats classes live about 4.79 miles away from Del Lago. And you can see that each of the different sample size sampling distributions for means is clustered around that value as well. So the population mean is also the mean of my sampling distribution of those X bars. So you can see this outlier and its effect it had on the shape of the graph. And as you take samples of size 5, we can see that those values probably randomly selected that outlier as part of their sample. Therefore, they got means that were a little bit larger than the rest of the means that are clustered closer to the true population value, true population mean. But as we take larger sample sizes, those larger sample sizes balance out that outlier better, so the values even cluster more towards the true population mean. So to summarize, pause here and see if you can answer these questions. Averages or means are either more or less variable than individual values. Averages are more or less normal than the individual values. And increasing the sample sizes either increases or decreases the variability of the sampling distribution. Pause here and see if you can answer these for yourself. All right, so averages and means are less variable than the individual values. They're less spread out. They cluster more towards the middle. And averages are more normal. My graphs start to look more normal when I'm taking averages rather than individual values. And increasing the sample size decreases the variability. I get less variability the bigger the sample size. This is important for concepts that we're learning next. So when we look at our sample mean distribution statistics, the mean of all my X bars, so if I take many samples and I average them, then the average of those many sample averages will be the true population mean, mu. And we would expect the standard deviation of those sample averages to be smaller because we saw from before that the values get less and less variable the bigger the sample size. So the formula for the standard deviation of sample means, if I took many samples and averaged them, ends up being the population standard deviation divided by the square root of n. That's the formula that can be derived. And what we see from that is as n gets larger, so as my sample size gets larger, the standard deviation will get smaller because as I divide by a larger number, the entire fraction gets smaller, so the entire standard deviation gets smaller. So this formula for standard deviation, though, only works if the 10% condition is satisfied, and you should recognize the 10% condition from before. It has to do with independence of each of the samples. So if my population size is greater than or equal to 10 times the sample size, then that satisfies that condition. So that's one of the conditions we have to check when we do problems later. Okay, normality. So a sampling distribution of sample means from a normal population is also normal. So if in the problem it tells you that the population distribution is normal, then you also know if I take sample means from that population, I will get a normal distribution of sample means. So if the original distribution has a normal mu sigma distribution, then the sampling distribution of your x bars, or sample means, has a normal mu because it has the same mean as the population, but the standard deviation is now the original standard deviation divided by the square root of n. Okay, another example we did in class is we took 750 pennies and we found their ages. The top graph is the ages of all of those pennies in the 750 pennies that we collected. You'll notice it's heavily skewed to the right. And if you think about that in context, it makes sense because you are more surprised to find a penny that is very old, for instance, born earlier than 1950, because as pennies get older, they start falling out of distribution. They get destroyed, they get lost, they get collected by collectors. So we should have more values in the smaller ranges. So our penny population distribution is highly skewed to the right. But then we took samples of size 5 and averaged those values. So if I take a sample of pennies of size 5 and find the average age of those values, notice that the graph gets less heavily skewed to the right and is more normal. And then furthermore, I then took samples of size 15 and the graph gets less and less variable and more normal. Less skewed to the right, more normal, and they're all centered around the true population mean of 15.68. So the means stay the same. The shapes change to more and more normal the larger the sample size, and the variability gets smaller the larger the sample size. So even though the population of ages of pennies is extremely skewed to the right, as we take sample means or sample averages, we see that the distributions become more and more normal as sample size increases. This is actually a theorem called the central limit theorem. If we draw an SRS of size n from any population with mean mu and standard deviation of sigma, the central limit theorem says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. Now the question is, how large is large enough? How large does my sample size have to be? So we have a rule of thumb for this. So the rule of thumb is if my sample size is greater than or equal to 30, we can invoke the central limit theorem, and you can abbreviate it like that, CLT, and call the distribution approximately normal. So even if the original population distribution was not normal, if your sample size is large enough, you can assume that my population distribution of the sample means, or my sampling distribution of the sample means, will be normal. So we have two ways to tell if a sampling distribution is normal. The first way is if it tells you that the population distribution is normal, then the sampling distribution will also be normal. And that's true for any sample size. But if it doesn't tell you the population distribution is normal, you have to check and see if the central limit theorem works. So if the population distribution is not normal, the central limit theorem, or CLT, tells us that the sampling distribution of x bar will be approximately normal in most cases if my sample size is greater than or equal to 30. Okay, we're ready for an example problem. So the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal with an average or mean of 266 days and a standard deviation of 16 days. Find the probability that one randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So we graph this. So we have a normal distribution, mean 266, standard deviation 16. And we want to see what's the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So in your graphing calculator, you can find a normal CDF and plug in. My lower bound would be 270. My upper bound is infinity, or 99999. And the mean is 266, standard deviation 16, and I get 0.4012. So we know that one randomly chosen pregnant woman has about a 40% probability of having a pregnancy last more than 270 days. Don't forget to write a in context statement. Don't just put an answer. We need to put the in context statement at the end there. Okay. All right, so that was a population distribution problem. Now we're going to see what if we're taking a sample. So this time we're not choosing one person at random from the population. We're choosing a simple random sample of 6 pregnant women. Let X bar equal the mean or average pregnancy length from the sample. So first we have to check the conditions that we talked about. Our first condition is this distribution of simple random samples of 6 pregnant women going to be normal? So in the original problem, it told us the population distribution is given as normal. So therefore, our distribution of samples means is also normal. So that condition checks out. Now, if in the original problem it didn't say the population distribution was normal, then we would have to try to invoke the central limit theorem. But we don't have to do that here. It could be of any sample size. So our first condition checks. Our next condition is it independent, so that we can use the formulas for standard deviation that we need. So in order for it to be independent, it has to satisfy this 10% condition. So is the population greater than or equal to 10 times the sample size? So the population is all pregnant women in the world. So I would assume that the number of pregnant women in the world is greater than or equal to 10 times 6, which is our sample size. So we're just plugging 6 into that formula. So this checks out because the number of pregnant women in the world is definitely greater than or equal to 60. So that's our independent condition that checks. Okay, so when you're doing problems like this, it's a good thing to make yourself a little table where you write down all the information you know. So we know that capital N is the number of pregnant women in the world, and we know small n is our sample size 6. We know that our population mean was given to us as 266, and since we're taking a sample mean, that mean will be the same as the population mean. Our standard deviation of the entire population is sigma equals 16, but our standard deviation of the means, our sample means, will be smaller because remember, sample means are less variable. So we use that formula, so we have to put 16 in for sigma and 6 in for n. And if we use our calculator to do that division, we see that's about 6.53. So our new standard deviation for the sample means is 6.53. So now we can ask a question about the sample mean distribution, the sampling distribution. So now it wants you to find the probability that the mean or average pregnancy length for the women in the sample of size 6 exceeds 270 days. Now be careful, this is very different than the first question. The first question said, if I choose one random person out of all the pregnant women in the world, what's the probability that person has pregnancy length greater than 270? This is now asking, if I pick 6 random women, what's the probability that the average of their pregnancy lengths will be greater than 270? So now I have to say, okay, my mean stays the same because the mean of the sampling mean distribution is the same as the population, but now my standard deviation has changed quite a bit. So that's going to be less spread out. I'm going to have probably a smaller probability, which I do. So we use the same normal CDF. The only thing that changes in here, my lower bound's the same, my upper bound's the same, my mean's the same. Standard deviation's the only thing that changes. And you'll notice that this new probability is smaller because because the distribution is less spread out, it's less likely to get an average that is so high. So the probability that a simple random sample of 6 pregnant women has an average pregnancy length greater than 270 days is about 27%. Make sure you write a little statement at the end in context. And to leave you with this, don't be mean, have an above average day. Normal Curvosaurus says bye.